In this video, we're going to go ahead and continue off of a previous video about Heegaard splittings. And what I'd like to do in this video is convince you that there are many different ways to poke holes in spheres in some sense. So what we're going to do is try to convince you that we can write R3 almost as a union of two balls. And to do that, let me go ahead and start with a single point, and then blow up that point with a whole bunch of concentric spheres centered on that point. If you let that radius go out to infinity, you ask what you get, and sure enough, any student of multivariable calculus will tell you this is going to give you all of R3. So you can even put this collection of spheres in the proper location so we can set up for later. But the idea for now is to find some clever way of splitting up R3 into multiple components. And one of the simplest ways that we can do this is to just go ahead and take the unit sphere, we'll call this one S2, right? Topological representation of the unit sphere is something called S2, the two-sphere. So we're going to use the unit sphere to divide R3 into two pieces. On one side, we obviously get a ball, and in fact it'll be the unit ball. And we'll go ahead and include that two-sphere boundary, so we'll make this a closed unit ball. But the question now is what lies on the other side? So let's think about this. If we were to consider what is outside of this ball, well, it's just going to be a whole bunch of this yellow stuff. It's going to be essentially just a blue region and a gold region. And while the gold region, I think, is pretty obviously just going to be every bit of R3 except for that blue ball in the middle. And let's go ahead and include the two-sphere boundary, so it's going to be another closed object. But R3 without a ball, I can tell you, I will show you, is really just a ball that's missing one point. And in fact, it'll be missing its center point for simplicity. So to see this, let's go ahead and draw what an open ball looks like. So open in one sense. It's a ball with a point missing out of the center. What you want to do with this now is invert that ball. So essentially just take the sphere of radius r and map it to a sphere of radius 1 over r. Since all the radii in this blue ball are less than or equal to 1, they will be mapped to spheres of higher radius or greater radius. So all that we have to do here to complete the ball is to just add a single point, right? Then we can go ahead and close up this open ball into something that we can work with. And the result is that R3 plus some other point. It's not going to be a point in R3, so don't confuse yourself here. It's just another object, another point. And what we get is effectively two balls that are glued together along the same unit sphere. And we saw this in a previous video, that this creates a Heegaard splitting for the 3-sphere. So if we go ahead and call this R3 plus a point the extended real three-dimensional space, then this is going to be equivalent to a Heegaard splitting, or not even a Heegaard splitting. It's going to be equivalent to the 3-sphere. Now, what we want to do from here is change up that representation of the 3-sphere. So let's go ahead and do something interesting. Let's core out along the z-axis. So what that really means here is we are going to take the blue ball and drill out this little yellow bar, this little cylinder in the blue ball, and effectively add it to the yellow bit outside. So let me see if I can't convince you of what object this might look like. The blue, I think, is easy enough to see. We have just poked a hole from north to south pole in this solid object. And this will be what I'm drawing on the right. So this will just be this cored out apple, so to speak. But what's happening in the gold here? The gold region, I can convince you, I think, all we're doing is just adding that little gold handle. And in order to smooth out that picture, let's go ahead and redraw it. So again, we're going to see a cored out blue ball and then a yellow ball with a handle, a solid handle attached to it. So drawing it a little bit differently this time. I'm not sure why I draw things differently from time to time, but you know, it's what works. So what we have officially created here, if I kind of smush out everything into a nice smooth picture, I get a pair of solid tori. Right, so donuts, not just the icing on the outside, this is the icing and the dough in the middle. So this is a pair of solid tori that are effectively creating exactly the same space. R3 hat hasn't changed, but our way of viewing it has. So we can view R3 hat, which is the same thing topologically as S3, something called the one-point compactification of that space, as either a union of two balls or now a union of two solid tori. And the interesting thing that we can do is we can keep punching holes in that sphere, in that ball rather, to include as many holes as we want. So we don't have to core out along the z-axis, but we do have to make sure we use chords in that ball. So if we take out neighborhoods of chords in the ball, then we can keep adding handles to the yellow ball, or the yellow ball. So we get one representation of S3 for each hole that we put into that blue ball, so the number of handles that we glue onto the gold one. So this first one we're drawing is the same one we've seen from this video, from a previous video. We have a union of two balls, or we've just seen we get a genus 1 representation using two solid tori. Now we can also get a genus 2, a two-holed representation of the three-sphere, by punching out another hole. So we can continue with genus 3, genus 4, but the point is that these are all what are called Heegaard splittings of the three-sphere. So the question that I want to pose to you, that I'd like to see if you see what you have to say in the comments, is like, are there any other representations, any other Heegaard splittings of S3? Can you use this picture that I'm drawing as inspiration to perhaps come up with a new representation of S3? Well, and how would you go about proving that you have the full list? Well, let me know in the comments. Leave a like, consider subscribing, and I will see you all in the next video.